let's now look a little bit on other assumptions. So we talked a lot about actually the ignorability assumption in randomized control trials, but there are actually other assumptions that need to hold a lot of the times, so we can estimate average treatment effects. One of the most important ones in causal inference is called the stable unit treatment value assumption, or SUTVA. SUTVA basically means that there's no interference and there's also no hidden variations of the treatment. What does it mean? It sounds kind of complicated. It's actually not that complicated. If you think about it, it basically means the no interference part, that the treatment applied to one unit does not affect the outcome of other units. So basically, whether I receive a treatment or not cannot affect someone else, okay? So basically no spillovers, okay, or externalities, as is often referred to. So imagine that we have two individuals, 1 and 2, okay? Z1 means whether individual 1 got the treatment or not, and Z2 whether individual 2 got the treatment or not, okay? Under SUTVA, what this means is that the potential outcomes of that unit, of that second unit, of unit 2, is independent of the treatment assignment of the first unit, okay? So again, if the first unit got the treatment, it doesn't really affect my potential outcomes. If the first unit did not get the treatment, my potential outcomes are exactly the same, okay? So this is like the mathematical sort of expression for this, but let's look at some examples, okay? Let's see what's going on here. Oh, sorry. Let's first look at what the other part of SUTVA is, which is no hidden variations of the treatment. This is a bit less talked about. The most important part, not the most important part, but the most talked about part of SUTVA is the first one, which is basically no interference. But no hidden variations of the treatment is also important, which basically means that an individual who is receiving a specific treatment level cannot receive different forms of that treatment. Again, complicated. Let's see with an example. Let's think about the headache example that we had from the previous class. So we have individual 1 now gets a new aspirin, right? Individual 2 gets an old aspirin, which let's say that is less effective. Let's call it aspirin minus. And we have individual 3 that doesn't get a pill, okay? If we just say that that the treatment is 2 different values, okay, Z0 if the person doesn't get an aspirin, and Z1 if a person gets an aspirin, whether it's new or old, okay? The problem here is that the potential outcomes would change depending on whether I got aspirin plus or aspirin minus, right? Thinking that aspirin minus is less effective, okay? So in that sense, if I have, if there's a probability for me to get either the new aspirin or the old aspirin, and we just label it aspirin, then basically depending on what aspirin I get, my potential outcomes would be different, okay? And again, we're thinking that under a treatment assignment, my potential outcomes need to be fixed. And that's the hidden variation of treatment in that case. So that's also important to consider. One solution to this would actually be to have 3 treatment levels, right? So to have a control group who doesn't get the pill, treatment 1, which would be like the old aspirin, and treatment 2, which would be the new aspirin. In that case, just by relabeling the treatment, I already don't have hidden variations on the treatment, and everything is solved and SUTVA holds, okay? So again, just think about that when you're thinking about how to label your treatments. Okay, so now let's look at the scenarios where SUTVA can fail. The first one, and most likely one of the most common ways that it can fail, is with what is called network effect. So as you know, people are not just islands, and they talk to each other, and they communicate with each other, and they interact with each other, and all of that can actually generate spillovers from certain interventions into other persons that are not necessarily treated, okay? So that would be a way that Sattva would fail. And the other way that's usually seen or especially thought of in economics is general equilibrium effects. Okay, so we're gonna see both of them. Let's talk a little bit about network effects. These are all often referred to as spillovers, and basically is when potential outcomes depend on who gets the treatment. So let's look at an example. We have the same study participants that we had before. They're very eager to participate again. But now, basically, what I'm showing is them sort of as a network, okay? So imagine that these two people that are participating in the study, these are a couple. This is a soccer team, for instance, so they're all very interconnected with each other and they talk to each other all the time. That's why the arrows go both ways and are very thick. And maybe imagine that if this is a school, I don't know, this is like a class president, so she talks a lot to a couple of other people and also is friends with this girl, okay? And we also have this random guy here who's actually not friends with anyone, okay? So he's not connected to anyone. So now let's focus just on these three participants of the study, okay? So we have again the couple and the loner down there. Let's assume that first we assign this guy here to treatment, and this couple we assign them to controls. Okay, so they don't receive the treatment. If we look at their potential outcomes in this case, this person would have 0 if they didn't receive the treatment and 1 if they received the treatment, while this guy here would have 1 if they did not receive the treatment, 3 if they did receive the treatment, and she would have 0 and 2 depending on whether she did not or did not receive the treatment or received the treatment. Okay, these are the potential outcomes. Remember that under a treatment assignment, they should be fixed. Remember that these potential outcomes should be fixed. Okay. Great. So if you estimate here the causal effect, for instance, taking just the average of the treatment group minus the average of the control group, you would see that this is 1 minus 0.5. So the treatment effect here will be 0.5. Great. Awesome. So again, remember that these potential outcomes 1, 3, 0, 2, 0, 1. What happens now if we change the assignment and instead of treating the lonely guy down here, we treat this guy, which is one of the people in this couple? Imagine that the treatment is information, okay? Information about anything. Maybe this guy, he got treated, and basically because he's connected to his girlfriend, he will just share the information that he got with his girlfriend, right? So basically, even though she's not treated, she was not assigned to treatment, she still got the information. So basically now, even in the control group, she has the same potential outcome as if she was in the treatment group because she got the same information, even though, again, she was not in the treatment group, okay? And this guy down here, again, he's not treated in this case. And he basically has a potential outcome that remains unchanged. So in this case, by whether treating or not treating his boyfriend, her boyfriend, the potential outcomes for this girl change. So that means that her potential outcomes are not independent of the treatment assignment of her boyfriend. So this is basically what is called spillover or a network effect, and this would break Sattva. Is there something that we can do about this? And this is important. One of the ways that you can basically try to avoid this network effect of breaking Sattva is to randomize at a higher level. So for instance, instead, if you think that people within a neighborhood are very interconnected or within a school are very interconnected, you can randomize at a higher level. So don't randomize people inside a neighborhood or a school, for instance, but randomize whole neighborhoods or whole schools. So a complete school would either be in treatment or control. Okay, in that way, everyone within that unit is treated or under control, and there can be spillovers between them. Okay, basically because they're either all in one group or in the other. The problem about this, basically, and we're gonna see it in the next few slides, is that you have to cluster your standard errors, and with that you lose a little bit of power. Okay, so basically you're not able to detect effects that are smaller. Clustering standard errors basically means that you are assuming that within this unit's neighborhood, schools, or whatever, there's a common shock, a common error term that moves everyone sort of in the same way. So in that sense, you cannot assume that every unit within this clusters are independent. That breaks, again, one of the assumptions that we had for standard errors that we saw on one of the first classes. So basically, to take into account that they're not independent within each cluster, you do what it's called clustering standard errors. We're going to see a little bit more about this when we talk about other observational studies, but just for you to have it on the back of your head for now. The second way you can actually take this into account is to actually model the network. This is way more expensive, way harder, because measuring networks is not easy. But as you could see from actually the homework, what Duflo and co-authors did was actually model the network using surveys. Okay, so if you can model the network and have these different degrees of centrality of how households interconnect and things like that, you can include those. Okay, also as confounders or things like that. And if you can model the network, then it's a way. Then you do not need to actually. You don't have a problem with identifying the causal effects in that sense. Great, let's talk about general equilibrium effects. Basically, this usually arises when you scale up a program or an intervention, which basically means that on a smaller scale, when you're not affecting sort of other things going on around you, the effects could be one thing, and then when you scale it up because of general equilibrium effects, the effects could actually change. Okay, so imagine, for instance, that you want to test the effect of providing information about employment and expected income to students to see whether it affects their choice of university and or major. Okay, so this is very common. You want to provide information to students. Think about, even within one university, about expected employment and income. Okay, if you do so for a small group of students, this could have actually important effects. Usually what happens is the students sort into majors that usually have better employment expectations and better income expectations. Great. However, if you provided this to the whole university, for instance, those effects would, or for a larger portion of the university, those effects would not necessarily be the same because there would be congestion effects. So imagine that economics or business, in this case, is one of the most sought out majors because of their employment rates and expected income, but it has sort of a fixed number of slots. If you give a lot of people that information, basically, they will all try to come to get those slots, and not everyone would be able to get those slots because, again, there's a limited amount of them. So the effects, even if you treat them, would not necessarily be the same because they would not necessarily be treated in that sense. There's congestion. So that would happen basically if we offered it to everyone.